Gas behavior can also be described using the kinetic molecular theory of gases. This again is something that we saw originally in Chemistry 1. If we think of the gas particles bouncing around inside a box, they are never stationary. They are always moving. They have kinetic energy, half mv squared. They have momentum, mv. They have mass, m. They have velocity, v. They are in constant motion. And if we think that the only source of their energy is thermal energy, then it would be tempting to think that they all travel at the same speed. But they don't. There is a range of speed. What we say is that the kinetic energy should be the same, but there's a range of speeds. And the range of speeds looks something like this. It's a bell curve, but it's skewed. It doesn't come back down to zero on this side. Now, if this axis is speed, there is no point at which time any of the particles have stopped moving. So we never have a situation where speed is zero. We do have a situation where there is definitely an average. That is the average speed of the particles. And we can also say that there is a point on this graph where these particles are traveling at excessively large speed. These are the high speed particles, and collisions at high speed, cause more pressure than collisions at average speed. Okay, so we have a slewed or biased Gaussian curve. What happens when we change the temperature? It flattens the curve. The peak is now not as popular. If this is amounts, and we were going to quantify amount later on, we didn't quantify it at all in Chemistry 1. We just said it can be whatever you imagine it to be. So what happens here is I've moved the new average velocity to higher, but I've also really radically changed the number of very high impact collisions that this sample has. And conversely, if we were to cool this down, then we move the peak to a lower speed, and in fact it will, because the area underneath the curve represents the total sample size, this peak would actually increase. So low temperature, medium temperature, red one is the high temperature. And when we say that the area underneath the curve represents the total amount of sample, that's a hint that there's an integration in the solution here. There's a one-page derivation in our textbook that starts with a particle approaching the wall, and it doesn't matter what the angle is, and then it bounces, and that the momentum in is equal to the negative of the momentum out. And then it throws a couple of other things into the equation. We talk about the mass of the particles and however many there are. And one page later, we get to the important part, that PV equals 1/3 N M V squared RMS. Okay, what this means is N right here is the number of particles. We use N in PV equals something N in another way to mean number of moles. Technically it's in here somewhere, but it hasn't been expressed yet because M is the mass multiplied by Avogadro's number. Okay, so number of particles, Avogadro's number is here, and VRMS is the velocity of the particle at the root mean squared, which is take the velocity, square it, and then take the root. Because we have a population of gas particles, we have a spread of velocities. This is our root mean squared value. It's our best average. Okay. Here, because there is a sub-definition for this. Capital M is a lowercase m multiplied by NA. NA is Avogadro's number and M is mass. Okay? So this gives us PV equals 1/3 NM V squared RMS. V squared RMS, which is a useful thing to figure out, is the square root of 3RT over M. And again, M is our mass multiplied by Avogadro's number. There's good news and bad news here. The bad news is this is complicated. The good news is someone else has already done all the work for us. James Clerk Maxwell and Ludwig van Boltzmann came up with this distribution, and this quantity up here that we've been just saying is amount versus V for speed. This can now be quantified as the distribution of speeds. Specifically, it's the Maxwell-Boltzmann distribution of speeds, and it follows this equation here, 4 pi m over 2 pi rt raised to the power of 3 over 2 multiplied by v squared e to the minus mv squared over 2 rt. Okay, so fairly complicated. There's only a handful of terms here, but they're used more than once. You know, temperature appears a couple of times, pi is in there a couple of times, velocity is in there a couple of times. The outcome here largely depends on this exponential term up here. That there's a v squared right here, and because we're squaring its effect negatively, that means that there are very few particles out here at the ultra high speed. Okay? So one of the outcomes is the number of particles with very high velocities is small. Small. Also, up here in this term, that negative value is going to be impacted by a mass term that says that as your particles get heavier, their velocities are likely to be smaller. So that's the skew that we would see if we increase the mass of our gas sample. We would skew this to the left-hand side. And here, because temperature appears in the exponential term here as a denominator, that kind of overrules the negative impact here of the exponent, so that when temperature goes up, velocity goes up. And we've seen that also as the skew. When we increase temperature, we skew this way. We see more at the high, very high velocities. Let's look at what we can do with this data. So we have this curve. The distribution of speeds follows this equation right here. And if I integrate this curve, I can find the number of particles underneath that curve. So if I wanted to know, hey, how many particles do I have here at the ultra high range, I would integrate only between these two velocities. If I wanted to know everything about this curve to find the average, the mean velocity, then I would integrate everything in this equation between 0 and infinity. So my mean velocity, that's a lowercase v, my mean velocity is the velocity and the function of the velocity multiplied by dv. And again, there's a derivation in our book. This is only like maybe a third of a page of what the derivation is, but it comes out to be the root of 8RT divided by pi m. And remember, m is the mass multiplied by Avogadro's number. This is really useful. This is a very nice simplification from something that is rather large. Software can do this. There are also tables of standard integrals that will help you get to this. We won't be deriving any information because it's already been done. Okay, now That's kind of similar to a value that we found just recently, that the root mean square velocity was the root of 3 RT over m. That means that the mean velocity is equal to the root mean squared velocity multiplied by this term, the root 8 over 3 pi. Here's some of the useful velocity information that we can pull from this graph. The mean velocity is the root of 8 RT over pi m. And because we already know what the root mean squared is, or if we already know what that is, then V mean equals VRMS multiplied by the root of 8 over 3 pi. Now, because our graph is skewed, it doesn't come back down symmetrically. Our mean is not the turning point. This is the turning point of the graph, where my derivative of that graph goes to 0. That's the dy by dx equals 0 at the turning point. So that's our most probable velocity. This is the most likely. And that is equal to the root of 2 RT over m, which would also be equal to the VRMS multiplied by the root of 2 over 3. The other thing that is here is that we can find this. It's called the relative velocity. And the relative velocity is useful when we think about collisions, because it is the speed at which two particles that are the same as each other approach each other. And that's V mean multiplied by the root of 2. If we know the relative velocity, the speed at which particles are approaching each other, then we can calculate the collision frequency, how often collisions between gas particles can occur. The collision frequency Z is given as sigma VREL n over V. Sigma here is called the collisional cross section, and it is pi d squared, where d is the diameter of your molecule or atom. V is the relative velocity, n is the number of molecules, and V is the volume. Okay, so there's an n over V in here, and we're in the chapter talking about gases. So what if that n and V right here were to substitute in, and we reformed this in terms of pressure? So I'm going to substitute in PV equals nRT in for this n over V term, and we get Z equals sigma relative velocity times pressure divided by KT. Now this has been lurking for a while, and it has finally popped up. The K is the Boltzmann constant, and the Boltzmann constant is nothing more than the universal gas constant divided by Avogadro's number. We've been talking about gases moving and their velocities and their masses, so it's best to think about R in terms of energy, where R is 8.3144 joules per Kelvin per mole, and Avogadro's number is 6.02 times 10 to the 23 per mole. So those go away, and R divided by Na is 1.381 joules per Kelvin. This is Boltzmann's constant. So gas particles that are in motion can really be doing one of two things. They can be colliding, or they can be not colliding, which leaves us one less thing to figure out, which is the mean free path. That is the distance, the average distance that a gas molecule travels before colliding with another molecule. It's given by lambda, and lambda equals VREL over Z. Lambda is the mean free path, VREL is the relative velocity, and Z is the collision frequency. Collision frequencies should be pretty large numbers, and they're per unit time. So think of, maybe hundreds of thousands, millions, even billions of collisions per second. Now, there is a Z in here that we had previously defined, and if I substitute Z equals sigma VREL P over KT in here, then lambda equals KT over lambda sigma P. Lambda equals KT over sigma P. Lambda is our mean free path, K is the Boltzmann constant, T is the temperature, T is always going to be in Kelvin. Sigma we had previously defined, and P is pressure. Give me a second to tell you what sigma is one last time. Sigma was the collisional cross section. And collisional cross section comes into effect because if your gas particles have large diameters, then they're more likely to hit each other than if they have very small diameters. It's as simple as that. Okay.